Why does AI learn at all? If machines are just math and code, what makes them improve, getting better every time they see more data or make a mistake? This fundamental question lies at the heart of artificial intelligence, driving its continuous evolution and increasing capabilities. It's not magic, but a carefully designed process of iterative refinement. The short answer is, we give AI a goal, provide feedback on how well it did, and apply updates that reduce error or increase reward. This systematic approach allows AI systems to adapt and enhance their performance over time, much like how humans learn from experience. This continuous loop, objective, feedback, update, drives the entire learning process for artificial intelligence. It's a dynamic cycle where each stage informs the next, leading to increasingly sophisticated and accurate AI models. First, the objective. We define what better means for the AI, whether it's classifying cats versus dogs with higher accuracy, predicting the next word in a sentence more precisely, or maximizing a game score to achieve victory. The objective provides a clear target for the AI's learning efforts. The model doesn't inherently want anything. It's engineered to optimize the specific numerical target we choose for it. This target could be minimizing a cost function or maximizing a utility function, all defined by human designers to achieve a desired outcome. Next, feedback. For prediction tasks, we compute a loss, a single number that tells us precisely how wrong the model was. This loss function quantifies the discrepancy between the model's prediction and the actual correct answer, providing a clear signal for improvement. Lower loss is always better, indicating higher accuracy. For decision-making scenarios, we assign a reward, where a higher value indicates better performance. This reward signal guides the AI towards actions that lead to more favorable outcomes in its environment. Feedback effectively converts the model's performance into a measurable signal, crucial for its continuous improvement. This signal acts as a compass, directing the AI to adjust its internal parameters and refine its decision-making processes. Then come the updates. Algorithms like gradient descent gently nudge the model's parameters in the direction that most reduces loss or increases reward. This iterative adjustment process is fundamental to how AI models learn and adapt. Imagine an error landscape where the gradient is the slope pointing downhill. By stepping a little in that direction again and again, the model finds regions of lower error and becomes more capable. Each small step contributes to the overall optimization, gradually improving the model's performance. Architecture determines what the model can easily learn. Convolutional networks, for instance, excel at capturing patterns in images, like edges, textures, and shapes. Their layered structure allows them to process visual information hierarchically, identifying increasingly complex features. Transformers, on the other hand, are designed to handle long-range relationships in sequences such as language, audio, or code. Their attention mechanisms allow them to weigh the importance of different parts of a sequence, making them highly effective for tasks requiring contextual understanding. With the right structure and the right data, these models can discover incredibly powerful regularities within complex information. This synergy between architectural design and data quality is what unlocks the true potential of artificial intelligence, enabling it to solve intricate problems. Data is the essential fuel for AI. The more diverse and representative the data, the more likely the model will learn general patterns rather than simply memorizing quirks. A rich and varied dataset ensures that the AI can generalize its knowledge to new, unseen situations. Scale matters significantly, as larger datasets often lead to more robust models. But the quality of the data is equally crucial for robust learning. Even vast amounts of low-quality data can lead to flawed or biased AI systems, highlighting the importance of careful data curation. Clean datasets, comprehensive coverage of edge cases, and careful evaluation are what truly separate robust models from brittle ones. These practices ensure that the AI is not only accurate, but also reliable and fair in its operations, especially in critical applications. There are three primary ways learning happens in artificial intelligence, each suited for different types of problems and data structures. Understanding these distinctions is key to appreciating the versatility of AI. In supervised learning, labeled examples guide the model to minimize prediction error, learning from explicit correct answers. This method is akin to a student learning with a teacher who provides direct corrections for every mistake, making it highly effective for classification and regression tasks. In self-supervised learning, the data supervises itself, like predicting masked words or the next token, unlocking vast unlabeled corpora. This innovative approach allows AI to learn from massive amounts of raw, unstructured data by creating its own learning signals, significantly expanding its training possibilities. Finally, in reinforcement learning, agents learn through trial and error, taking actions, receiving rewards, and optimizing for long-term return. This paradigm is particularly powerful for tasks involving sequential decision-making, such as game playing or robotic control, where the AI learns by interacting with its environment. Success isn't just about achieving low training error. It's about generalization, doing well on new, unseen inputs. A model that performs perfectly on its training data but fails on new data is not truly intelligent. It has merely memorized the training examples. We encourage generalization through diverse data, regularization techniques, and validation that accurately mirrors real-world conditions. These strategies help prevent overfitting and ensure that the AI's learned patterns are broadly applicable and robust. Overfitting looks perfect on the training set, but ultimately collapses when confronted with the unpredictable shifts of reality. This phenomenon highlights the critical importance of building models that can adapt to variability rather than just replicating past observations. Understanding these core principles helps us grasp the simple truth behind how smart machines learn and evolve. It reveals that AI's intelligence is not mystical, but a product of well-defined objectives, continuous feedback, and iterative updates, all powered by vast amounts of data and sophisticated architectures.